Ladies and gentlemen, my name is Jan Kec. I work in SVUM Research and Testing Center for Materials, and as an external student I prepare my PhD thesis and CTU. Let me present my paper entitled Oil Transition Pipeline with Corrosion Defects Reinforced by Two Types of Sleeve. Special effort has been taken to comparison of efficiency of sleeves. This article was written with cooperation of my colleague from SVUM. Here you can see outline of my lecture, which will be compiled from introduction. Subsequent experimental result will be described here, and the most important findings will be evaluated in conclusion. The most of oil pipelines operating in Czech Republic are more than 4 decades old. It's common that the integrity of many of them is affected by various types of defects. The most common type of defects are corrosion losses on the outside and the inside of the pipelines. The presence of defects on pipeline results in reduction the safety and reliability of the section. The most reliable way of making the pipeline safe again is to replace the entire affected section, but this entails a number of costs. A less expensive way to ensure the safety and reliability of the pipeline is reinforced with a sleeve. Two types of sleeves are used in Czech Republic pipelines: the cold lock and the clock spring. They are mainly used to repair the corrosion defects. The clock spring is a composite sleeve consisting of glass fibers and polyester resin. The cold lock is the steel sleeve with composite filling. The aim of presented work is to verify the stress-strain states of the pipeline after repairing by the sleeve, determine the residual strength of the pipeline with the sleeve, and to verify the efficiency of sleeves. The pipes taken into account are shown in the figures. The pipe with nominal diameter 500 mm and a wall thickness 8 mm was reinforced with a cold lock sleeve, and the second pipe, nominal diameter 700 mm and wall thickness 10 mm, was reinforced with a clock spring sleeve. Both pipes are seamless and made of X42 steel. Two corrosion defects of 75% and 63% of wall thickness were found on the outer surface of DN500 pipeline during operation. The defects were repaired in 2000 with the two cold lock sleeves. The pipe was operating with the cold lock sleeve until 2020, subsequently cut out and subject to the full-scale test. Before the pressure test had started, the pipeline was shortened to the 5 meters and both ends of pipelines were covered with caps. The drawing of pipe is shown in the figure. The measured pipe wall thickness and strain gauge position are marked in the drawing. A similar drawing of DN700 pipe is shown in the figure. Internal corrosion defect of 79% of wall thickness were found on the pipe during the operation. The defect was repaired in 2000 with a 300 mm wide cold lock sleeve with 6 layers. The girth weld was located 250 mm from the edge of the clock spring sleeve. The pipe DN700 was operated for 2 decades with the sleeve. In the figures you can see the unique pipeline testing system. The pipes are pressurized with water from a water pressure pump. Servo valve is controlled by PLC computer to maintain the pressure within the set range. The full-scale test consists of three parts. The first part was a static loading of the pipes with 4 dwells up to the yield strength for the stress-strain analysis of the bare pipe and the sleeves. This was followed by a fatigue test with the pressure range between 2 and 6.3 MPa with total 10,000 cycles. The last part was the burst pressure test, the results of which enabled to determine the limit states, burst pressure and position of fracture. In the figures you can see the strain response at the internal preservation of the pipe to the specified minimum yield strength. The almost linear response to pressure was observed with a maximum volume 1600 microstrains measured on circumferentially oriented strain gauge T1. The difference in strain between the lowest and highest wall thickness is negligible. Strain response at the cold clock sleeve is also linear. The values of maximum strain are 1/3 lower than on the bare pipe. It's suggesting a good reinforcement by the sleeve. On the circumferentially oriented strain gauge T1, high plastic deformation development during the last dwell. A significant difference between the lowest and the highest wall thickness was observed. In general, bulging of pipelines was very inhomogeneous. It is probably due to inhomogeneity of the wall thickness. To compare efficiency of two sleeves, the stress-strain ratio of the bare pipe and the sleeves were calculated to uniaxial stress using von Mises criterion. This comparison can be seen in the figure. It can be seen that the cold lock sleeve has a reduction in strain about 70% compared to the bare pipe, which can be considered as good a reinforcement effect of the sleeve. However, for the cold click spring, the highest strength can be observed on the sleeve than on the bare pipe. Due to the bulging of internal corrosion defect, it can be seen that the ratio of strain on the sleeve and pipe decrease when the increase in pressure. The sleeve suppresses the bulging of the corrosion defect. The fatigue pressure test followed the static pressure test. The pressure range was between 2 and 6.3 MPa with the total number 10,006 cycles, which correspond to about 27 years of operation at frequency 1 cycle per day. Each cycle had a sawtooth shape, as can be seen in the left figure. No strain increments were observed on the monitored strain gauge during the fatigue pressure test. No leakage of the pressure media was observed for the tested pipe. The burst pressure test was performed with a gradual increase of internal pressure up to the destruction of pipe. Stress strain curves and the pressure curve is shown in the figures. The yielding appeared around 11 MPa on strain gauges located on the surface of DN500 pipe. For the clock lock sleeve, a change in orientation of longitudinal strain above the yield strength can be observed. Above the yield strength, the strain starts turn towards the lower values. Until then, the complete transition to negative values occurs, which is a result of material bulging at the surrounding of the sleeve and the introduction of additional bending. Arrow indicates the step change In the pressure, the reinforcing effect of sleeve has disappeared and the sleeve has failed. At the pressure 10.4 MPa, the stress-strain behavior of clock spring sleeve change. Up to the pressure 10.4 MPa, the strain response of strain gauges is linear. Above this value, the character of longitudinal strain gauges changes considerably, and they started to take negative values. Surround the material of pipe pressures to the sleeve and thus introduce additional bending as well as compressive deformation. The pipe after burst test can be seen on the figure. The DN500 pipe with clock sleeve was filled at the pressure 16.9 MPa on the bare pipe. On the other hand, the failure of DN700 pipe with clock spring occurred at the pressure 15.7 MPa at internal corrosion defect. Conclusions. A significant reinforcement effect was observed on the clock sleeve, where a stress reduction of 70% was observed compared to the bare pipe. The higher strains were observed on the clock sleeve than on the bare pipe, which was attributed to bulging of internal corrosion defect. For the clock sleeve, the reinforcement effect of the sleeve increased with the increasing stress. Both sleeves complied with the fatigue test for 10,000 cycles without leakage. Residual pipe strength was favorable for the both pipe, corresponding to 2.8 times maximum allowable operation pressure and 3 times maximum allowable operation pressure for DN700 with the clock slope and the DN500 with the clock sleeve respectively. The grant of Ministry of Education, Young and Sport of Czech Republic is gratefully acknowledged. Thank you for attention.